All right, my friends, section 11.4 is called Limits at Infinity. Let's give you a warm-up to get you started here. Let's have you evaluate each of the following limits. First one, the limit as x approaches infinity of 1 over x. And next, limit as x approaches infinity of 1 over x squared. And let's look at the limit as x approaches infinity of 100 over x. All right, my friends, go ahead and think about what you think the answers are, and then we can talk about it. All right, my friends. So the first one, the limit as x approaches infinity of 1 over x, you've got 1, and then it's divided by a number that is getting larger and larger and larger in magnitude. So you could actually illustrate this using a numerical approach by just doing 1 divided by, say, 1,000, 1 divided by, say, 10,000, 1 divided by 100,000, and just kind of show the progression as you divide by numbers that are increasingly large in magnitude, and then look at what the results are going to. And hopefully you're okay with these being scientific notation. This is 0.0001, and this is 0.00001. Anyway, so the point is that your values are getting increasingly closer to 0. So by the time you reach infinity, this value will reach 0. Anyway, so as your x value approaches infinity, this value is approaching a value of 0. A little bit of unnecessary nerdiness. If you ever see a superscript plus sign on your 0 there, it just means that you're approaching 0, but from above or from the positive side. But I'm going to take that off because right now that is very unnecessary nerdiness, and so it's best to just say 0 here. So next one, the limit as x approaches infinity of 1 over that number squared. So I hope it makes sense that this would equal 0 as well. It's even approaching 0 faster than this one did. The limit as x approaches infinity of 100 divided by x. So for this one, if you're not sure, you could use the constant multiple rule for limits and factor the 100 out. And then notice that the limit that you have here is the very first limit expression that we talked about. So your answer would be 100 times 0. And so if you were thinking that 100 divided by a number approaching infinity was going to be 0, then you're dead right. As a matter of fact, I hope it makes sense. Even if you had a really big number up here, like, 100,000, as long as it's a constant, it could have been factored out. And so any finite number, even if it's a really big finite number, any fixed finite number that is, divided by a number going to infinity would go to 0. Okay, so this is going to be fundamental for the thinking that we're going to go through today. So now let's move to example 1. So for example 1, let's say you are given f of x equaling, let's say you have 3x squared plus 1 over 2 minus x minus 5x squared. And we're going to do this in 2 parts. So part A, let's say I ask you to find the horizontal asymptote. Okay, and there are a number of ways of doing this. You will have learned this in Algebra 2, and then we reviewed it in Chapter 2 in Pre-Cal. Sometimes it's not until now that people really understand it. So what you were told on a rule level was if the degree of the numerator is the same as the degree of the denominator, then you will have a horizontal asymptote, and the equation will be y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. So you would have a horizontal asymptote at y equals -3/5. And if you remember that, then that's great. And if you don't remember that, that's going to be okay, because part B, we're going to explore another way to get the exact same information. So for part B, let's have you verify your answer to part A using an infinite limit. Okay, so let's talk really quick about this on a conceptual level, because if you just think of this as a kind of first you do this, then you do that type thing, you're likely to get to the test and have all your techniques kind of messed up a little bit. So let's talk about, first of all, what on earth does this answer up here for part A even mean? Okay, so it means that the graph of f of x, if your horizontal asymptote is y equals -3/5, it means that y equals f of x starts thinking it's that horizontal line when your x values get very large in magnitude. So let's think about that. So if let's say I was to graph f of x, and I'm not going to do an exact graph here, okay? But let's say I did. So I'm going to go ahead and put a dashed line here, horizontal. And let's say that this is y equals -3/5. And you don't have to put this in your notes unless you find this incredibly enlightening and you want to. But this part doesn't really have to go in your notes. And then if you were to graph this, then I don't know, you'd find the y-intercept, you'd find the vertical asymptotes. Let's say it has a couple vertical asymptotes. I have not done the math to verify that it does, but let's say it does, because most of them did. And then you would find x-intercepts or the lack thereof, and you could figure out kind of what the graph looks like. Okay, so, all right, let's say you did all the work and you graphed it. Now, all I really want to look at here is the significance of this being your horizontal asymptote. If y equals -3/5 is your horizontal asymptote, then what that means is, let me fold up this piece of paper, is that if you were to cover up, to fold it better, sorry, if you were to cover up the inside part, all the fun swoop-de-doo parts where the excitement happens of your graph, and then just look at your graph as x gets really large in magnitude, this function literally starts thinking it's a horizontal line. It starts thinking it's y equals -3/5. Well, since that's the case, then that could lead you to know what to do for part B. Part B, we're going to take the limit as either x approaches infinity or -infinity. It wouldn't matter, so I'm going to pick infinity of the function rule. And we're going to show that you still get -3/5. So to that end, if you're asked to find a horizontal asymptote using a limit process with rational functions, you could simply take the limit as x approaches positive or negative infinity, your choice. I'm going to pick infinity, of the rule that you use to get y values. Okay, now let's talk about evaluating this limit, and that's an important part of this lesson. If you let x go to infinity, if you were to try the direct substitution method, which with something like infinity you probably shouldn't do, but you would get 3 times infinity squared plus 1, which I claim is infinity, or approaches infinity. And then on the bottom you'd have 2 minus infinity minus 5 times infinity squared, which I claim approaches -infinity. Now, a lot of folks would look at this fraction and say, aha, infinity, the infinities cancel. So your answer is -1. But I'm here to tell you this about that. Not all infinities are the same size. We're about to find that the top number approaches infinity at a rate of 3/5 at which the bottom number approaches infinity. So this, my friends, just like 0 over 0, is an indeterminate form, which means you're going to have to work on it a little bit to figure out what it really equals. So with that said, here's a little move, and it's really, this little trick really only applies if you have x going to infinity or negative infinity. So don't try to use it if like x is going to 0 or something like that. But what you can do is take your original limit statement and multiply by a creative version of 1. And the creative version of 1 that will work each time, you're going to look at the degree of the denominator. That's right, the degree of the denominator. And then you're going to multiply by 1 over x to that power over itself. Notice that I'm just multiplying by the number 1. It's a fancy version of 1. And so I'm going to make this look different, but it won't have a different value. So now, copy your limit statement and then distribute 1 over x squared in, and then cancel as you go. So 3x squared times 1 over x squared would reduce down to 3 because the x squareds would cancel. Then distribute that in, 1 times 1 over x squared. On the bottom, 2 over x squared minus, here the x will cancel with one of those x's, so you'd have minus 1 over x. And then minus, and the x squareds would cancel, so you'd have 5. Now notice, by turning this fraction into this unsightly compound fraction, if I let x go to infinity now, I don't have an indeterminate form anymore. Let x go to infinity on 3, you still have 3. Let x go to infinity on 1 over x squared, you get 0. X going to infinity of 2 over x squared, 0. Of 1 over x, 0. And of -5, still -5. Simplify this and you get, surprise, surprise, -3/5. And this is the work that it would take to verify that what you were told in Algebra 2 actually works. Okay, now a lot of people, when I show them this limit process, they kind of get grumpy because they feel like what they learned in Algebra 2 is way easier, and you are dead right. It is way easier. But if I do this right, then you're actually going to understand that you are finding the exact same thing in Part B and Part A. So that means that if you're ever asked to find a horizontal asymptote, even if it's of a rule where these Algebra 2 rules would not apply, you could use this limit process. And then you're also supposed to understand that let's say you're on the AP exam for calculus in a year, and they ask you to evaluate this limit, then you could use your Algebra 2 rules, show no work at all, and boom, know the answer. So the two methods are interchangeable. And so you want to know how to do each ideally, okay? But if you were to only know one thing, I would probably go with the limit process because it'll get you a lot farther. If we start throwing square roots on top of expressions and things like that, then you have to say bye-bye to your Algebra 2 rules, but this limit process would work each time. All right, my friends, example 2. Let's say that you are given this time g of x equals x to the 4th over 3x to the 6th plus x squared minus 9. And for part A, you were asked to find the horizontal asymptote. Okay, review from Algebra 2. So degree of the top is 4, degree of the bottom is 6. So the degree of the numerator is less than the degree of the numerator. The rule that you would have learned in Algebra 2 is that you would have a horizontal asymptote at y equals 0. And if you remember that, then that's wonderful. Now for part B, let's tie this into infinite limits. So let's have you verify your answer from, not form, but from part A using an infinite limit. Okay, so to do that, we'll take the limit as x approaches. You tell me, we're talking end behavior here. Yep, infinity of x to the 4th over 3x to the 6th plus x squared minus 9. If you tried direct substitution, which is really kind of a no-no when it comes to infinity, you will get an indeterminate form of infinity divided by infinity. So instead, we're going to create a cosmetic change here. So we're going to multiply, look at the degree of the denominator, it's 6. So we're going to multiply by 1 over x to the 6th over itself. And then just distribute that in and reduce fractions as we go. So we'd be left with the limit as x approaches infinity of 1 over x squared over 3 plus 1 over x to the 4th minus 9 over x to the 6th. Okay, now that we have this crazy compound fraction, let x approach infinity and see what you get. And you should have something that's more certain than what we had if we had tried it from the beginning. Let x go to infinity on 1 over x squared, you get 0. X going to infinity of 3 is 3 plus 1 over x to the 4th. If x goes to infinity, goes to 0. 9 over infinity to the 6th power also would go to 0. We're left with 0 divided by 3. And what's 0 divided by 3? It is 0, which matches what we found using Algebra 2 rules. All right, my friends. Example 3. Same type of deal. This time, given h of x equals x squared minus x minus 13 over x minus 4. Part A, let's have you find you guessed it, the horizontal asymptote of that function, just using Algebra 2 if you remember it. And then if you don't remember it, you could just fall back on what we're doing here in part B. You are going to verify your answer using an infinite limit. Okay, and I'm hoping that if these are things that did not make total sense in Algebra 2, that we can actually help them make more sense just by using the calculus that we're doing today. Okay. So, finding the horizontal asymptote. Algebra 2, the rules were look at the degree of the numerator, which is 2, look at the degree of the denominator, which is 1. This time the degree of the numerator is greater, and so that was the condition for having no horizontal asymptote. So this graph does not start thinking it's a horizontal line on the far ends. Let's verify that this is true by using an infinite limit. So if we take the limit as x approaches infinity of x squared minus x minus 13 over x minus 4. Again, if you look at the degree of the denominator, which is 1, and use that to create your creative version of 1, so 1 over x to the first power, and then distribute it in. We'd have the limit as x approaches infinity of then just multiply and cancel as you go. X minus 1 minus 13 over x over 1 minus 4 over x. Let x go to infinity, and then look at what we'd have. If x goes to infinity here, you'd have infinity, take away 1, take away 0, over 1 minus 0. Simplify this. What's infinity take away 1? It's infinity over 1. So what did we just find? We just found out that if you go to the right forever on your graph, that the y coordinate approaches infinity. So what would that really tell you? It would just kind of tell you some general end behavior stuff. It would tell you as you go to the right, the graph actually pops up. It does not flatten out and become a horizontal line. As a matter of fact, you may recall that if the degree of the numerator is exactly 1 greater than the degree of the denominator, you would have what's called a slant asymptote. And this is something that if this didn't make total sense last year or earlier in the year, then let's make sure it makes total sense now. So for part C, I think I'll fit it here. Let's have you find the slant asymptote. Okay, so step 1 was to take your improper fraction. And why is this an improper fraction? Because the degree of the top is not less than the degree of the bottom. And you're going to write it in mixed fraction form by simply dividing the top by the bottom, which is what that fraction bar means in the first place. So you're basically going to take x squared minus x minus 13, and you're going to divide it by x minus 4. So let's do that. Keep your eye on your front term. And so x times what would make the x squared drop out? X. And then distribute fully. So we'd have x times x is x squared, x times negative 4 is negative 4x. And then we're going to subtract the whole row. So x squared minus x squared is 0, which was our plan all along. Negative x minus negative 4x, that's like adding 4x. So we'd end up with 3x. And then we're going to drop the negative 13, and then just repeat the process. X times positive 3. Now let's multiply that out. 3x minus 12, subtract the whole row, and then you'd end up with, I think, negative 1. So what does this work tell me? It tells me that this function rule is exactly the same as x plus 3 minus 1 over x minus 4. These two things are exactly the same. Punch that in on your calculator, punch that in on your calculator, you get the exact same graph. So how do you find the slant asymptote? Well, a slant asymptote is end behavior just like a horizontal asymptote. So look at this answer here. If I was to let x go to infinity, look at this remainder. Infinity minus 4, infinity. 1 divided by infinity, 0. Which is why what we told you in the beginning of the year to find the slant asymptote is you do long division and you disregard the remainder because it was going to go to 0 anyway because it's your end behavior. So your slant asymptote would be the line y equals x plus 3. I hope that makes sense. It also backs up what we found over here. If you think about y equals x plus 3, as it goes to the right, it goes up forever. And so that would back up your answer that you had over here. All right, my friends, that's section 11.4, at least shorter than the other sections. Hope everything's going great, and I hope you guys ask me questions if you have any. Take care, everybody.